Hello again. So in this part of the lecture, we are going to discuss the equivalent circuit for an induction motor. The starting point would be the realization that at standstill, each phase of the induction motor is equivalent to a single phase transformer with its secondary winding short-circuited. Hello again. So in this part of the lecture, we are going to discuss how to come up with the equivalent circuit for the induction motor per phase. It is important to realize that the starting point is the realization that at standstill, each phase of the induction motor is equivalent to a single phase transformer with its secondary winding short-circuited. So assume, just for simplicity, that we have something similar to an ideal transformer where the turns ratio is equal to 0. So this is just referring back to the transformer. Remember, we had the primary resistance and reactance and the secondary resistance and the reactance. In a similar manner, we are going to come up with the equivalent circuit of an induction motor. However, the difference is that the presence of the air gap over here, makes the magnetizing current has a significant effect and cannot be ignored. However, the core loss resistance may be removed from the equivalent circuit and its effect accounted for by including the core losses in our calculations. So how can that be done? This is done by referring the rotor circuit to the input terminal. And in this case, the induction motor per phase equivalent circuit would be shown like this, where RS is the stator copper loss, the R is the rotor copper loss, and over here in this resistance will result in the mechanical power, and this would be the output mechanical power of the motor. Over here we have the magnetizing reactance and the iron losses. Over here is the voltage input per phase. So remember that if we have values for the equivalent circuit parameters, then we can calculate the mechanical output power and hence the torque. And based on these, we can also calculate the efficiency of the motor at any given speed or slip at a specific supply voltage. So that will be the goal in the next few slides. All right, so to understand how to come up with this equivalent circuit, we have to split the circuits for the rotor and the stator. So let's consider that the rotor is rotating at a given slip. Remember that there is a relationship between the voltage of the rotor induced in the rotor and the voltage of the source, and that relationship is given by multiplying the source voltage with the slip S. Now, if the circuit of the rotor, so this is the circuit related to the rotor, it contains the rotor winding losses as well as the reactance, the inductance reactance. Remember that the inductance reactance, it is related to the frequency, and this frequency over here, it is related to the frequency of the source. So we can say that the frequency of the rotor is equal to S multiplied by the frequency of the source. Now, having this information in mind, we will answer the next question, which is how to bring the rotor terminal into the primary or the input terminal. To do so, first we need to calculate the voltage induced at the rotor, which is equal to the slip multiplied by the voltage of the source. So consider this as one loop of a circuit. We are able to calculate that voltage by using Ohm's law or around the loop. So if we assume that IR is the current induced in the rotor, then this means that the voltage across this terminal over here, it is equal to the current multiplied by the resistance of the rotor plus the same current IR multiplied by the inductance reactance over here. So we will have this equation if we take IR as a common factor. Now let us find what is Vs on its own without S. So what we will do is we will divide the whole equation by the slip S. In this case, we will have on the left-hand side only Vs, and on the right-hand side, we will have the relationship of the voltages across R and across the inductance reactance, and we will have the resistance of the rotor winding divided by S. So now that we have Vs, we will bring this circuit to the primary side over here, and it will look something similar to that. So if we bring it, let's now open this. So this component will go into here, and this component will go over there. And that's how we can see that the rotor circuit and the primary circuit, or the stator circuit, now they are connected together. However, also remember that in between there is an air gap. Okay, now let us do some arrangements. Now we can find the equivalent inductance reactance by adding the inductance reactance of both the stator and the rotor. We can see that the total per phase power, which crosses from the stator to the rotor, is represented by this R over S component. So this is the power that crosses the air gap. And remember that the electrical input power per phase, as you have taken before, is the phase voltage, the stator current multiplied by cosine phi, where phi is the angle between the phase voltage and the stator current over here. Now, having the equivalent circuit and its components will help us calculate the mechanical output power. So we want to understand how much of a mechanical power this motor produces. So first, let's start by calculating the total per phase power which crosses the air gap. Remember that the component that affects the power is this component over here. So once the power crosses the air gap, we can say that its value is the rotor current square multiplied by the rotor resistance divided by S. So we call this the power that crossed the air gap per phase. Now, if we want to calculate the total power for the three-phase, we just multiply that value by 3. And then we have the three-phase power, which crosses the air gap. Now remember that there are some rotor copper losses, and these are given by the value of the resistance of the rotor winding. And this can be calculated for the three-phase by multiplying 3 with the current of the rotor square and that resistance. Now notice that this is related to the power that crosses the gap. So we can say that the power due to the rotor copper losses, so this is a power loss, right? It has gone through the rotor winding. We can say that it is related to the power gap with the parameter S. So it is equal to the P gap times S. Now finally, to calculate what is the mechanical power produced by the motor, we can say that it is equal to the power that has crossed the air gap minus the power loss due to the winding of the rotor. And if you substitute these values over here, right, you will get this equation. Now, this means that we can also say that the mechanical power is equal to the power of the gap times 1 minus S. So you can see that this slip has a big and a direct effect on the mechanical power that is produced by the motor. Alright, so now let's put everything together from start till the end. So we will be looking now at something called the power flow and the losses. So starting from the right beginning, from the electric input power, which is a three-phase, the input power to the motor is given by this equation over here. So this is the phase voltage, the current in the stator, and this is the power factor. So after that, there are some iron losses. This is due to RC, and it can be calculated by this equation for the three-phase. There are also some stator copper losses due to RS, which is the resistance of the winding of the stator. And once we cross the air gap, that is the power which crosses the air gap that we have just calculated, there will be some losses due to the rotor copper in the motor, due to RR. There will be also some friction and windage losses, and after that we will be getting the mechanical output power. So this is actually what you will have at the shaft, and this what will draw the load. And the power of the shaft is equal to the mechanical torque times omega, where omega is the actual motor speed in radians per second. Also, notice that the mechanical power, it is the result of the shaft power. So that's what we are interested in. That's what reaches the load. And the power that is dissipated in the friction and the windage. Okay, so I think we are now ready to solve an example. And this way you will understand better the relationship of these parameters and how to calculate them. So take a look at this equivalent circuit. Given its parameters over here, shown in this table, so you are given all of these parameters, the stator winding resistance, the rotor winding resistance, the magnetizing reactance, the iron loss, and the equivalent inductance reactance. You need to determine the following parameters for a three-phase, six-pole machine rotating at 900 revolution per minute and operating off a 240 volt, that is a phase voltage, at a 50 hertz supply. So this is the frequency of the source. We need to calculate the slip, the air gap power, the mechanical output power, the motor torque, the total machine losses, and the motor efficiency. Also, you have a slight note over here to neglect the friction and the windage loss. So let's get started. We will do this example together, and then I'm going to give you another example to solve and practice on your own after that. Okay, so the first parameter we need to calculate is the slip. Remember that in order to calculate the slip, you need to know the synchronous speed. We already have the speed of the rotor, which is given, that is 900, but we do not have the value of the synchronous speed. To calculate the synchronous speed, we need to get back to its formula that we have looked at in the previous lecture. It is related to the frequency of the source and the number of the poles. So putting these parameters into this formula, we will get the synchronous speed to be 1000 RPM. Now take this value, insert it in the formula of the slip, you will get the percentage, so S as a percentage, which would be 10%. So we have number 1 done. All right, now moving on to the next parameter, which is the power that has crossed the gap. In order to calculate this parameter, we need to find first the value of the current in the rotor, which is denoted by IR. So in this case, in order to find the current, we need to understand how its value is related to the phase voltage and the equivalent impedance. So let us get back over here. We can notice that the voltage across the terminals over here is equal to the all the voltages that has been dropped across the different components. So this means that if we want to calculate the current, in this case it would be easier to calculate I square rather than I, because if we calculate I, we will have to take into consideration the phasor values, in this case the magnitude and the direction of the current. But because only we need at this particular moment the value of IR square, we can calculate it as the voltage of the phase square divided by the magnitude of the impedance, which is the two resistors in series square plus the equivalent reactance square. Then plugging the numbers, you will get the value of the current in ampere square. Now taking this value and plugging it here, we will get the value of the power that has crossed the gap in watts. Now if you are not sure about how we got this value over here, you need to get back and understand how to calculate the magnitude of a phasor value. The third parameter we will be calculating is the output mechanical power, which is given, as we saw earlier, by this formula. So now that we have the current in the rotor, the resistance of the rotor, and the slip, we can plug these parameters into the formula and we will get the value of the mechanical power. The fourth parameter we want to calculate is the mechanical torque. Remember that the mechanical torque is equal to the mechanical power divided by the speed of the rotor in radians per second. So now that we have the mechanical power over here, we can divide it by the angular or the speed of the rotor in radians per second. So we have the speed of the rotor in RPM. We convert it to radians per second by this formula. And then we will have the value of the torque in Newton meter. Remember that in such questions, writing the unit is highly important. And if you didn't put it, you may lose some points which are related to the unit. The next parameter we are going to calculate is the power losses. Remember that the power losses, they are due to the losses in the rotor windings, the losses in the stator windings, and the iron losses. So if we combine all these three and multiply them by 3, because we want to have the total power, not only the single phase power, but the total power, we are going to get that value in watts. The final parameter to calculate is the motor efficiency. The efficiency is equal to the mechanical power, which is the output power. Remember in the question they told us to ignore any winding or friction losses. So that's why we didn't subtract them from the mechanical output power. Otherwise we would have to subtract them if they if they were given in the question. So again, getting back to the efficiency, so it is the mechanical output power divided by the summation of the mechanical and the power losses. Again, putting the numbers that we have calculated over here, we will get the efficiency to be 70%. And we can say that the efficiency of this motor is 70%. Okay, so now it is your turn to solve an example. Let's read the question together and then I'll give you some time to solve the example in pairs. So you are given a 3-phase 4-pole machine operating off a 460 volts and 60 hertz supply. Has the per phase equivalent circuit parameters shown in table 2 and the equivalent diagram shown below. So this is the equivalent diagram of the circuit. In this case, R1 is the stator resistance and this is the stator reactance. Over here, this is the rotor reactance and R2 is the rotor resistance. If the total rotational losses are 1100 watts, so notice that these are the rotational losses, which means that they are as a result of the resistance in the rotor. The core loss due to RC is lumped in the rotational losses, so you can consider them only as one component. For a rotor slip of 2.2%, determine the following. So you need to calculate the rotor speed in RPM, the stator current flowing in here, which is indicated as I1 in ampere, the mechanical power in watt, the shaft or the output power in watts as well, the motor torque in Newton meter, and the motor efficiency. You may also neglect any friction and windage loss. I'll give you about 10 to 15 minutes to try to solve this on your own, and then we can go through the solution together.